Hello and welcome everybody to another Applied Flow Technology webinar. I'm glad you could join us. If you're joining us live or if you're watching a recording, hopefully we'll find a good use of your hour and see how we can better improve our AFT Impulse runtime. My name's Nick Vastine. I'm a business applications engineer here with AFT, and hopefully we're all in the right place. And here today we're going to be learning about Impulse runtime and really understanding the back end of AFT Impulse so we can strategically make changes to our model to improve runtime without destroying our accuracy. Ultimately, our models will hopefully be better, faster, stronger. So with that in mind, let's jump into the agenda. So this will really start from the back end of why AFT Impulse needs to be a separate analysis product. Why does a transient solver differ from a steady state solver? And what implications does that have on the solver itself? So we'll look at what the transient solver is doing. We'll look at some of the underlying solver back end. And the first part of that is how do we section a model? So it's one of the 5 essential steps in creating an impulse model. One of them is sectioning your pipes. Usually that'll be sectioned for you, and it might not be a particularly difficult choice of how many sections to include. But by understanding what sectioning is, we can also see how that'll impact our runtime, which in this case, we're trying to optimize. Generally, if you're trying to improve your runtime, you probably have an existing model already with some runtime concerns, or at least looking for better efficiency in modeling your system. So we'll look at some of the pitfalls that may be within your model that we can isolate and recognize, and therefore try to troubleshoot to improve our runtime. So we'll look at why these minor issues within a model may ruin your runtime and ruin your sectioning as well. We'll talk about the trade-off between accuracy and runtime. So a lot of the things we'll talk about here will make changes to your model. And anytime you make a change to your model, you're introducing some uncertainty. That uncertainty may or may not create significant inaccuracy in your model, but it will increase your runtime. So you always have to evaluate the trade-offs, and we'll look at our example and if it impacts our accuracy at all. Finally, we'll take a look at some other approaches to further improve your runtime. The first 4 will largely be focused on what sectioning is and how we can optimize a model for sectioning. But there's some other small places where we can find better efficiency just by applying some logic to how we're defining a model. So to get into it, let's take a look at what a transient solver is and why that might be different than a normal steady state solver. So why is transient analysis harder than steady state? Generally, in steady state, you're taking a system with a collection of boundary conditions, and you're finding one solution that meets all of those boundary conditions, maintains mass continuity, energy continuity, all of that. But transient analysis is much harder because any change you make to the system, it's not immediately going to transition to a new steady state. In our case, we can look at how signals might take time to travel through a system. By a signal, that's sort of any change or any deviation from steady state that might transmit through a system. A typical example might be a waterhammer pressure rise due to a valve closure. That pressure rise isn't going to immediately transfer through the entire system. Instead, it'll incrementally travel based on something called the wave speed. So the wave speed is the inherent speed limit of a signal within a system. It's a very creative name, I know. The speed of the wave is the wave speed. And it takes time for that signal to transmit through the system. How do we capture that with a transient solver? Because a steady state, it doesn't matter incrementally. It's only looking at boundary conditions and how to meet those boundary conditions. So how does our solver capture this signal transmission because the signals are taking time to travel through the system? In this case, we use the method of characteristics. Now, this can be its own topic. People, I'm sure, have written doctoral theses about it. But for our purposes, we're going to define it as adjacent points informing one another over time. So for example, you would have a collection of points. For example, in a piping system, this might be different points in a single pipe. depending on how the points next to each point change, over time that'll impact how that point changes. So if, for example, we had a pressure rise here, in the next time step, we would expect to see a similar pressure rise in the next point, in the next time step, a similar pressure rise in the next point. But if you always think about adjacent points and how they inform each other, that's really what we're looking at with a transient solver. So the method of characteristics, it's a bit more complicated than that, but for our purposes, we care about how we can get this nice fine grid, so that way it's much easier to see how these points are informing one another over time. So again, if we think about the grid and in terms of sectioning, we can take that grid process and apply it to a piping system. So imagine that we have a pipe in our system. We can cut this pipe into different sections, so that way we have these adjacent points that'll inform one another over time. We can set this section length somewhat arbitrarily, but it'll generally be determined by sectioning within Impulse. That's why it's one of the essential steps in the model creation process. And to see how that changes over time, again, we look back at the wave speed. So the wave speed is the fastest time that a signal, a pressure change or a change in flow rate, can travel through the system. So it'll change a certain amount of x over a certain amount of time. If we rearrange that wave speed equation, we can look at our section length. We can divide that by our wave speed, and that'll give us an approximate time step for our method of characteristics. So that means after one time step, we can see how our signal will transmit through another section. So if this is our initial signal, after one time step, it'll move 1 delta x. Similarly, after another time step, it'll move over another section, so on and so forth. So by creating this grid and knowing that the wave has to travel at some maximum speed or at this speed consistently, independent of the size of a change of the signal, we can take advantage of sectioning to create this transient analysis to see how this signal moves through the system over time. So if we think back to that method of characteristics graph, it's sort of like we have our different points, our different adjacent points that are informing one another. And over time, we can see how those points move through the system to inform one another. Again, this is a pretty gross oversimplification of what Impulse is doing, especially when you consider things like frictional losses between sections or different components. But understanding that cutting it into sections is to create this grid. So that way, over time, we can create a signal and see how that signal is transmitting through the system. What our sectioning is going to do is create a bunch of calculation points. So while we're really trying to optimize for runtime, runtime is more of a metric of how many calculations that the solver needs to do. In this case, if we look at our pipe, we have about 8 sections, or in this case, we'll look at the solids as sections. So we'll have 7 sections to calculate over our 5 time steps. That's 35 calculations. We could rearrange our section length to make it much longer, in which case we would have 1 calculation over a much longer time step. So balancing how a system and how a model is sectioned is really where we're going to find the majority of our runtime efficiency improvements. So this is the core tenet of the webinar. A lot of the changes we're going to make are essential, or understanding sectioning is essential to understanding the changes that we're going to make to a model in order to optimize this sectioning. So we're not through with it yet. We can also take a look at how time step is going to change based on our wave speed and based on our section length. Again, we have this definition of wave speed where it's going to travel a certain distance over a certain time. More sections that you add are going to make each section shorter, and shorter sections means less time for the wave to travel between sections before you should be calculating it again. So again, we can look at how we define time step in the previous slide as our change in distance over our wave speed. The more sections we have, the shorter the section, wave speed will stay relatively constant, which means our time step will become much shorter. Here we can look at it a little bit more visually, where we have twice as many sections on the right than we do on the left. And based on our wave speed, we can see that we'll travel one section in one time step. This is great. If we wanted to continue on, we would see that same pattern we saw in the previous slide. But now if we create the same signal in this right system where we have twice as many sections, not only do we have to calculate more sections, but we have to calculate them more frequently. So the wave is going to travel half this distance, or half the full distance in half the time. Therefore, we need to update this intermediate point more often. So for the same distance that the wave has to travel, we'll call that delta x. Here we have to do many more calculations than on the left-hand side. It's also not a proportional increase. So on the right, we could see we would have 1, 2, 3, 4, 5, 6 calculations, whereas on the right side, we would have 6 on the top, another 6 in the middle, and then another 6 to reach the same point. So 6 on the left, 18 calculations on the right, leading to a much more significant runtime the more sections that you're adding. So because sectioning and time step are linked by this wave speed, that can lead to an exponential increase in the number of calculations. One, because you're calculating more sections in each pipe. And because there's shorter sections in each pipe, your time step is necessarily shorter, leading to more intermediate calculations through time. So there's more sections, there's more time. How does this all play into runtime? Ideally, we want to minimize the number of calculations when optimizing for runtime. Optimizing for accuracy may be different, and as we'll see, some of these changes may impact your accuracy and how we can address that. But the intent of this webinar and the intent of why you're all here and trying to improve your runtime is how can we reduce the number of sections in our model, which will help us, 1, reduce the number of calculations in each pipe, and 2, help us get larger time steps so there's less intermediate calculations. So why is sectioning a concern, or why would sectioning within your model cause some issues and cause a longer than anticipated or longer than is efficient runtime? One option is you may have very small pipes, which will make very small sections. One thing that you can do is try to fold different component losses into the pipes themselves, or combine different small pipes together. So if, for example, you had a system with a pipe, then a globe valve, and then another pipe, if that globe valve isn't participating in the transient, it may be okay to fold that loss into a pipe and increase the overall section length. A similar concern is that it's hard to make very small pipes have similar sections. So within a impulse model and within the method of characteristics, they're all going to have the same time step. That's fixed across all of the calculations, across all the pipes, independent of diameter, roughness, wave speed, a lot of those considerations. So if we took, for example, a very small pipe, such as a 1.5 foot pipe and a 2 foot pipe, you're going to introduce a lot of variance between those two. So here, for example, an ideal section may not be 1.5 feet because now you have to round this pipe much more aggressively than you may have to a larger pipe. In this case, you may have to use 1/2 foot as your section length, in which case now you have 3 sections and 4 sections instead of ideally a 2 foot pipe and a 2 foot pipe, each at 1 section. So with those additional sections, all that's going to exponentially increase your runtime. This is where you can look for those small changes to a model that won't significantly increase or impact accuracy, but can drastically improve your runtime. So a lot of these examples we'll look at in a model to see what we can look for and what changes we can make. But this is one consideration to make, is looking at small pipes, small length pipes within your system. Another central conflict is if you mix very short and very long pipes in the same model. Again, if they're using the same time step, generally that section length will be similar. So if, for example, we had a very short 0.1 meter pipe, for example, if that was between a pump and a check valve, where it's somewhat arbitrary how long that pipe is, followed by a 1,000 meter pipeline, that can cause some issues in your model for issues that'll quickly become apparent. So let's say that we have one section in our 0.1 meter pipe. We have to apply that same section length to our 1,000 meter pipe, and now we have 10,001 sections that we need to calculate for every time step. And with such a short length, our time step is also going to be incredibly short. So mixing very small pipes and very large pipes are going to cause issues. And now if we look at instead shifting or increasing our number of sections for improved accuracy, generally what we'll see with users is they will start their model, they'll go to section pipes and accept the minimum number of sections. You may run into a case where you want to run a model with more sections. It may improve your animation results. That'll be a common case. But if you're doing that for improved accuracy, it's much less marginal improvement in your accuracy. And in some cases, it may even make your results worse, such as in cavitation, where a vapor pocket may exceed your section much more rapidly the smaller your section is. Usually that minimum number of sections will be determined by a variance. That variance is if we took a 1.5 foot section and put it into a 2 foot pipe, we have to round that into an integer number of sections. How that varies from the calculated number of 2 divided by 1.5, that'll determine how many sections are required in your system. So it's accounted for in that sectioning process. Going above and beyond that, while it may improve your accuracy, it's going to drastically increase your runtime, again, because that runtime is exponentially going to increase with increasing sections. So those are some of the potential pitfalls that you may, even now going through the webinar, think about within your own models. How can we address those concerns and try to improve a model for runtime? We'll look at some of the least drastic changes you can make to the model, as well as some of the most drastic. And generally, the more drastic the change you're going to make, the more runtime you're going to improve. But again, the question of how accurate is your result will always come up, which we'll address a little bit later in the webinar. So the least drastic option to improve your model is to combine pipes where possible. This will actually come up as the waterhammer assistant, which you may be familiar with when you start your run. In essence, you have a collection of pipes that you could join together and fold the losses into, increasing your overall potential section length. So in this case, if we had a pipe connected with a branch, connected with another pipe, if there's no losses in this branch, then we can fold those two pipes together, increasing our overall potential section length. We'll take a look at what this looks like in an example, which you can do from the analysis window and the section pipes window. Another potential option is to integer all your pipes. So this will help reduce a variance in your pipe sections, especially for short pipes. If we think back to our 1.5 foot versus 2 foot pipe model, if we rounded up that 1.5 foot pipe, then both of those pipes will be a closer order of magnitude and can have similar sections. In that case, it'll be a 1 foot section instead of the 1/2 foot section, which can help improve your runtime. And rounding your pipe to the nearest meter or foot, that can certainly help. Again, if you're modeling pipelines in lengths of miles, it might not be a good assumption to round to 1 mile, but you could go to the nearest 1/4 mile or 1/10 of a mile. Another potential option is to use a minimum pipe length. So this overcomes the issue we see with very short pipes and very long pipes in the same system. One could argue that the losses through a 0.1 meter pipe from the pump to a check valve is going to be generally negligible to the much larger losses you'll see through a 1,000-meter pipe. So by increasing those very short pipes very marginally, setting some sort of minimum pipe length, what that does is it helps us create a minimum section that we can share across our different pipes. So then, for example, instead of a 0.1 meter and a 1,000-meter pipe, if we used a 10-meter and a 1,000-meter pipe, now we only have 100 sections in our large pipe instead of 10,000. So bringing down the number of calculations several orders of magnitude, that'll certainly help you improve your runtime. Finally, you can round to a common multiple on all of your pipes. This is very similar to integering all of your pipes, where you're really rounding to 1, but you can take that even further. You can round to the nearest 5 meters, the nearest 10 meters. So if, for example, in our system, we'll be rounding to the nearest 10 foot, that'll make every pipe in your system have neat, uniform sections, all based on that smallest pipe. And that'll help improve your calculations because, one, it'll reduce the variance as well. And hopefully the increased loss that you're creating in your system is pretty negligible compared to the overall losses of your system. So all of that in mind, let's take a look at an example and see if we can spot some opportunities to improve our runtime. This will be a pretty simple example, but a lot of these same principles can apply to a full-scale system. You know, the more pipes, the more complicated it's going to be. But again, you're going to get even greater return on your runtime by implementing these things with all those different pipes. So here we have a pretty simple system where we're pumping from a reservoir to 2 deposits. We can see we have very precise length specifications down to 1/10 of a foot. And here we can see some potential points of conflict already. So here we see the shortest pipe in our system is 1.5 feet. Our longest pipe in our system is almost 1,700 feet. So if this is 1 foot, or this is one section is 1.5 feet, we already have more than 1,000 sections to calculate in just this pipe. We can also see a potential conflict in different small pipes where we have 1.5 feet here and 2 feet here. That'll cause some issues with variance, where we're trying to make both have similar length sections, but without rounding one or the other too drastically. That could lead to a section length of only 1/2 foot, which will triple the number of sections in pipe 15, again, really compounding the issue. We can see that we have some arbitrary division between different pipes. Generally, this might be due to specifying an intermediate elevation. So if this branch is slightly higher than this reservoir, we don't want to draw our pipe going direct from this valve to this reservoir. But by combining these pipes, we can fold that intermediate elevation or any intermediate losses into the pipe as well. That'll help us improve. So we're going to take a look at this example and we're going to try to isolate the different factors that we can do to it to see how it'll improve our runtime. So first we'll take a look at combining our different pipes. So we can look at combining pipe 4 and pipe 5, 14 and 15, pipe 2 and pipe 16. Those will all be recommended by Impulse for combination. So this should be a layup in terms of runtime improvement, because Impulse 1 tells you where they all are, and 2 will do all the combination for you, as we'll see. We can also set pipes to integers. So here, if we round pipe 2 to 2 feet, pipe 13 to 2 feet, pipe 3 to 3 feet, that should marginally help us improve our runtime, because now we don't have as much variance between the different systems. We can try setting a minimum length where we can set pipe 3 to 5 feet, pipe 13 to 5 feet, and that will set a better minimum section length instead of basing it all on 1.5 feet or 2 feet. And finally, the most extreme approach, we can round all the different pipes within 10 feet. So for example, we can round this pipe to 390, to 80, to 100, 180 or 1,680 rather. And that will help us create a very neatly sectioned model where we know the section length is about 10 feet. And that'll drastically improve our runtime compared to the initial half-foot or 1-foot section that we started with. So with all of those things in mind, first we want to set a benchmark and put some concepts in play. We won't actually be running the models during the webinar. Again, it'd be kind of ironic to sit and watch a model run while we're trying to optimize model runtime. So we've done some prior runs of these different cases where we'll look at the base scenario as we've seen the model already. We'll look at how we combine the pipes, integer the pipes, set a minimum length, and then finally, and most extremely, round all of the pipes to about 10 feet. Our starting runtime for that relatively simple, I believe, 16 or 17 pipe model is 300 seconds, which is about 5 minutes, which is pretty significant. You can imagine in the design process, if you made a small error in how you specified something, or if you're trying to batch run different scenarios, this runtime can get in the way of your analysis. So here we can see our section length is half a foot. We have 5,000 sections with 83,000 time steps, leading to a lot of calculations and therefore a very significant runtime. So we'll see how each of these facets compare. We'll see how that runtime hopefully falls to a more reasonable level. And after that, we'll take a look at if any accuracy was lost in this particular system. So all of that said, let's take a look at our model. Here we can see our reservoir through our pump, again, going to these two deposits. The transient in this case is one valve is closing slightly and one valve is opening. So we're changing the flow path of this system. And a lot of the time, these changes that you'll make, the impact that they'll have on results depends pretty significantly on what type of analysis that you're doing. One thing that we can do, sort of how I created that figure, is you can use visual report to quickly see the length of all your systems, or the length of all of your pipes in your system. Now, if we show, we can see at a glance any potential causes of concern, such as our very short pipe and our very long pipe, a lot of that analysis that we just went through. We can do the same thing from model data, where we can look at the length specifications here. We zoom in a little bit, we can see a lot of this marginal specification where specifying 2.675 of a foot, it may be useful for capturing all the different nuance within a system. And especially if you have the information, you're more likely to implement it, but it may not prove as useful or as marginally useful during transient analysis. So our first change that we're going to make is combining pipes. So we'll create a child scenario so we don't have to recreate the whole system. We can go ahead and section our pipes. If we update our results, here's where we can see a lot of those same concepts that we were discussing. We can see the length of each pipe, the wave speed. If we take that relationship, we can determine the ideal number of sections. We can then round that and determine the variance. So if we instead look at one pipe, we can see that an ideal situation would have an ideal number of sections of 1.6, but we have to round that to 2, which leads to various or significant variance in our sectioning results. So that's what this check is doing. It's going until it sees that it's within reason, and then moving forward with that calculation. Usually, as a user, I imagine people will run this, accept the default, hit OK, wonder why their runtime is so large, and then attend webinars like this. So hopefully we're all moving forward together and we can all make our models all run faster, which will improve engineering efficiency. So if we defined our system as intended and we combined, or we sectioned it, we looked at our transient analysis, and we go to run the model, we can see that we get this pop-up for the waterhammer assistant. So the waterhammer assistant is checked each run before each transient run. And it's telling you that we can dramatically improve your runtime by combining those pipes into larger pipes. So again, what we just discussed. It also shows that you have a very large number of sections in that longest pipe, and that you can improve runtime by ignoring things with the shortest section. In this case, our connection from our pump to whatever this branch was representing. So we don't want to continue with our run. We want to go and improve our runtime. And we do that from the section pipes window, where in the upper right, we see that we can combine our pipes, and that combining pipes can dramatically reduce the model runtime. Sounds like that's working in our direction. If we click combine pipes, we can see which pipes will be combined into the upstream pipes. We move this window a little bit, we can see that we have pipe 15, which will be merged into pipe 14. So that's good, it's just connected by a branch. We can see pipe 16 will be merged into pipe 2, which is great because this is our shortest pipe. That'll help us improve our sectioning. Similarly with pipe 5, that'll be merged into pipe 4. So if we hit OK, we can see that they all merge together. And now if we resection our pipes, now we don't have 3 sections in our controlling pipe, now we're down to 2. So with that 30 seconds of reading the error message and combining pipes that Impulse has recommended, let's take a look at how our runtime would improve. So just by combining pipes, we've reduced the number of sections required. Now our section length is 1 foot. That significantly reduces our total number of sections. It helps us increase our time step, reducing our total number of time steps and reducing our overall calculations. So just by combining those 6 pipes into 3 pipes, we've cut our runtime by 2/3. So great marginal improvement. Again, it's that exponential relationship with sectioning and runtime that instead of working against us, as we might complain about usually, we can now use it to work for us. So the next thing we're going to look at is moving all of our pipes to integers, and we'll see how that impacts our runtime. So again, we'll create a child scenario. We'll integer our pipes. And from model data, what we can do is go into each of these and round it to the nearest foot. And we'll see how that impacts things. So instead of 7¼ feet, we'll do 7 feet, 392 feet. We'll round this guy up to 3 feet. This guy up to 469. 2 feet's great already. And 1772. So obviously it'll be a bit more extreme the larger your model is to make those different changes. So it may not be as fruitful just to integer the pipes. It may be better to round them to a multiple of 5 or something. But for the proof of concept, we'll just integer them by 1 foot. We take a look at our visual report. We can again do our length, and we can see that now everything is a nice round number as well. So how does that impact our runtime? And again, these runtimes will also depend on some other factors. For example, if you're streaming a webinar, that'll increase your runtime, and depending on the processing power of your computer. But what we want to focus on here is the relative changes between runtime. So our combined pipes was pretty good. We got it down to about 1.5 minutes for runtime. Now, if we integer our pipes, we're down to 78 seconds. So we do see some marginal improvement with the number of sections required, but our section length is still 1. So we're inherently still going to see many sections through those long pipes and many calculations for our short time step. Our next improvement is looking at minimum length. So we have a few pipes in our system that we should increase because these are what's setting the minimum section for all of these other pipes. Again, think back to the 0.1 meter pipe, creating all of those sections in our 10,000 foot pipe. By increasing that minimum, we can reduce the overall number of sections, improving our runtime. So here, again, we'll create another child scenario. We'll call this rounding. We'll call this minimum length. We'll say 5 feet is our minimum. And again, we can go in here and update these to 5 feet. One thing that we can do instead, so let's say that we have a very large model with many different small pipes in it. And instead of going tediously through each one because we're not cleanly rounding, we're setting them all to one single value, what we can do instead is use global pipe edit. So let's actually reset this to 3 feet. And this will drastically help you in a much larger system where there's many small pipes to change, and marginally so in a much smaller system. So if we go up to the globe at the top, we can go to global pipe edit. And here, instead of remembering which pipes were below 5 feet, we can use special selection. And we can base our selection type on pipe input properties. Here we can change our pipe property to pipe length, and I want everything less than 5 feet to be selected. So you can imagine if we had a very large system, you can expand this out and automatically select a bunch of pipes. Or if, for example, we wanted to do a 10-foot minimum, that would also include pipe 1. So here we'll round to 5 feet. We have both of our pipes selected. We can select our pipe data, and we will set them to 5 feet. We then select the parameter we want to apply that selection, hit OK. And now if we look, we can see we have our minimum 5 feet. So it's less glamorous when there's only 2 pipes that you had to change. But if you extrapolate out, imagine your giant models, that can certainly be a time saver as well. So if we update these 2 pipes to 5 feet, what is that going to do for our runtime? We've gone from 5 minutes down to about 1.5 minutes to a little over a minute. And now by setting a 5-foot minimum, we're down to 18 seconds, which is great. So we can see how our total number of sections keeps falling off, our section length keeps growing. Our time step similarly increases, reducing the total number of calculations that we have to perform. So something that we could do even better is if we rounded all of the pipes to 5 feet, but if we want to be really extreme and see how low we can get this runtime down to without completely destroying the model, we can round our pipes to 10 feet. So that'll be our final experiment. And that we can do, we can actually run this one from Impulse, which will be exciting, I know. So we'll call this scenario rounded pipes. We'll say 10 feet. And here we'll just do it by hand because we're rounding by hand. But if you have a very large model, you can also use an Excel change set, in which case you would export a lot of this information. You would determine the pipe number. You can export the lengths out, use the round function in Excel to round to the nearest 5 or 10 or what have you, and then re-import those changes so that way it's all updated automatically. So again, there's a lot of marginal improvement that you can make just by slightly rounding each of these pipes, and it shouldn't significantly impact our results because the amount of loss that we're adding or removing isn't significant to the overall system losses. So now we have everything rounded. We can go ahead and resection our pipes. We see now we have one controlling section. Everything looks ideal. A very low variance where it's rounding from the ideal number of sections to the integer number of sections. You can hit OK, double check our transient control, and we see our runtimes down to predicted 1.14. Let's see if we get that. Ooh, just barely under. So all of those changes were pretty short changes. I mean, we did it within the past 10 minutes, or we could have made all of those changes within 2 runs of our base scenario. That's another way that we can put it into perspective. So if we go back to our table, we fell all the way from 5 minutes down to 1.4 seconds. So it looks like my computer was having an off day. Looks like it's doing even better now. We're down to 1.1 seconds. But here we can see how the total number of sections falls dramatically because of our new minimum section length. Our time step is an order of magnitude better. increasing or improving our total number of time steps, and reducing our total calculations by a few orders of magnitude. So again, this is the most drastic change that you can make to your system, and it'll get you the most drastic return on your runtime, but it can also create the most uncertainty in your system as long as, or depending on the assumptions that you have going into these changes. So whether your changes are conservative or not, that's always an engineering consideration, which brings us to the big question on everyone's mind, the thing that I've been alluding to this whole time. So faster models are great. Reducing runtime is a noble pursuit, but what's the catch? So any changes to your model, that's inherently going to introduce uncertainty. That pipe that we changed wasn't 1,770 feet, it was 1,772 feet and 0.625. So whether that change is significant to your system is going to inform how much uncertainty it'll introduce into your results. So it'll always be a trade-off. The more runtime that you throw at something, the more accurate it'll be. That's why something like CFD can be incredibly accurate, but it'll run for several weeks at a time. So we want to maximize our returns to runtime with minimal losses to accuracy. So if, for example, we look at our system where our transient was changing those valve positions to change flow to the different paths, we can see that our original has that same initial peak flow rate, and we can see similar end flow rates as well. And we can see the same case in the optimized case. But funnily enough, these were actually switched, but to a common user, you're not going to be able to tell that, right? Now, this is a pretty simple example. Flow rates to each reservoir may not be as significant as your maximum pressure due to a valve closure. So the moral of the story is it's always best to test these things for yourself. You can do sensitivity analysis and see if the changes that you make by rounding to 10 feet or creating a minimum length are significant enough to change your engineering conclusions. Every system is going to be unique, so what may work for my system in this case might not work for your system. So accuracy is important, obviously, but getting results in a reasonable amount of time is also important. We have some other considerations you can use to improve your runtime. This is somewhat related to sectioning, but you change things within the model a little bit differently. So if you're not as comfortable rounding pipes or setting a minimum length, these are some things that you can do to find small pieces of efficiency. So the first example is reducing your transient duration. So the transient duration is if I close this valve over 5 seconds, I want to see the results through 30 seconds. By reducing that transient duration, you're going to directly reduce the number of calculations you do, thus directly reducing your runtime. If, for example, you're achieving a new steady state within 10 seconds, it's not ideal to set a duration of 10 minutes because a lot of that time at the end is just going to be wasted calculating steady state. It's not tracking how a signal is moving through a system because everything is equilibrated. 10 minutes is a bit of an extreme example, but same concept applies if you have a 30-second transient. Just use engineering judgment there. Another potential area to improve your runtime is to start these transients as early as possible. So modeling steady state at the beginning of your transient simulation is just a waste of transient calculation effort. Again, you're not tracking how a signal is transmitting through the system, so you don't really need a method of characteristics-based solver to do that modeling. Generally, what we would recommend is starting your transients at time 0, in essence, making steady state as short as possible. Finally, you can start from an intermediate steady state. So let's say you have a 2-part valve closure and it reaches a reasonable steady state in the middle. You can instead change how your system's defined and create another scenario where that's your new starting point. Now you don't have to model the first part of the closure because you know you're going to reach that same point every time. So these are all things that don't change your model inherently. They're not changing your sectioning or anything like that. But just by rearranging it and understanding what the solver is doing, you can find some runtime efficiencies by minimizing the number of calculations that you have to do. So it's a lot to take in, I realize, but let's take a look at a summary of what we've learned here today. First thing, and I think the most important thing, is pipe sectioning has an exponential impact on your runtime. The more sections that you add to your system, not only the more calculations do you have per pipe, but the shorter your time step is going to be. So you're really double fold in how you're being impacted. So both time step and section length, they're all linked by the wave speed. Because they're linked, changing one inherently changes the other. There's a few ways that you can improve your runtime. Some of the ways that we looked at today was combining your pipes, which is the easiest and can provide a lot of marginal improvement. You can use pipe minimum lengths. Again, if you have very short pipes in your system with very long pipes, the short pipes may not contribute significant loss to the system. You can round pipes to multiples, and that'll give you really capitalizing on sectioning there. But a lot of things you can do within the model without changing the model itself, such as the transient duration and minimizing your steady state modeling time. Finally, changes to your model will change your results, but it might not be as much as you think. It's always important to test with your model of your system instead of going solely off what we've talked about here today. Again, it always relies on engineering judgment to understand the changes to your model and their impact on results. Whether that is going to change your engineering decisions is always going to be its own conflict of interest, right? So hopefully this was a good use of your time. Hopefully with what we've learned today, you can go out into the future and save at least 47 minutes on your future run times, in which case we would have broken even, which is pretty good. I want to thank you all again for attending. I know it's a lot to spend an hour with us, but hopefully it helps you improve your models. Of course, if there's any questions that we weren't able to answer, you can email them to webinars@aft.com. We'll do our best to get a response to you and answer your questions. If you have a model and you have a support subscription, you can also take a look and send that in. We'd be happy to take a look. Finally, if you have any ideas for future webinars, you can submit a topic. We're always looking for new topics and really seeing how we can make these webinars best for our users. So we'd love to hear from you. Thanks again for everyone for attending. If you have any questions, don't hesitate to send them our way. Thanks again.